his face because Springer did it in the first inning.
Or Bregman.
Or Bregman, yeah. And then afterwards, did like 2 reactions. Bregman was apologizing for it, and Soto was just like there, and he's like, "Yeah, I saw him do it," and I was like, "Why haven't I done that before?"
Because like my electives for like refreshment and
He's fun.
stats 252. Yeah,
It was like Bregman tried to hand it to his coach. Coach had no idea what was going on, drops it. Soto just goes out, and then before the coach tries to grab it, just drops it right in front of him.
Second one will religion and philosophy. Radar with our requirement, but then he was like, Chinese really good. Like, in his copy of the requirement. It's just weird if it's like a drop one of your LSC, so I was like, that sounds good.
Okay, so the plan today is to talk about a couple examples that illustrate things in chapter 14, possibly transformations, possibly trying to decide if something's linear or not, use of analysis of variance, and then extensions to more general linear models. And so just briefly, registration is coming up, it's imminent here. So there's a number of courses within math, statistics, data science, CS that could be relevant. Hope you consider those. Within computer science, some of you have taken the CS 111 either as part of math or statistics or data science. There'd be follow-up computer science ones. They also have an artificial intelligence one that relates to decision-making, automatic decision-making and searching, and it's implemented in a number of ways, so that might be interesting. Within data science, there's a Data Science 202, which is this computational methods class. Initially we had CS 202 and Statistics 202, and then we said we should actually have some data science labeled courses, and the DS 202 is the computer side and uses Python for doing a number of things. The DS 203, which is this fall, and should repeat next fall, uses R and is more a statistical application class for data science. All right. There is an introduction engineering in the math department. In terms of the math courses, there are a number that would be relevant for statistics or data science, theory of computation, graph theory, for instance. Some of the majors require proofs. If you're going into something with biology or life sciences, sometimes differential equations can be very helpful. In statistics, some of you I know have taken probability, but haven't taken probability. That would be a relevant course for things. But yeah, most of the other things in the spring are introductory at this point. So as you consider courses, I encourage you to consider the full range of courses in math, CS, statistics, and hope to see you. Hope you find some of those useful or interesting. So just a little plug for considering more in math and statistics. And what we want to do today is look at a couple of examples. But any questions about courses and majors or general things that you might think about? Don't need that right now. There is a homework due Friday that has a problem from chapter 13 and one from chapter 14. And so just a reminder that's there. Code is online. You can use the code to do many things and write up interpretations and things like that. In terms of the examples, right? Let's start in looking at those. The first, in chapter 14, it does this two-way analysis of variance without replication, so just one per time. And I found one example in a book called Biometry by Sokol and Rolf. It's kind of for a number of decades, has been a kind of first statistics course taken by graduate students in biology, field biology, wildlife biology, and other places. And actually, it was the first time I was a teaching assistant. I was assigned to Museum of Comparative Zoology. And they're teaching assistant over here, and this was the textbook that they used. So they have one example here about the temperature on some place called Rot Lake. It sounds like a really great place. So it could be one of the authors going out and taking measurements in the afternoons on 4/8/1952. And they did something at 10 different depths in the lake. Right? And so to enter the data from that book, I set up a data frame. The 4 days are there consecutive. The depths are 0, 1, 2, up to 6, and then it jumps to 9, 12, 15.5, and those are in meters, so that's 45, almost 50 feet, probably 50 feet deep at the bottom. So the thing they measure is the temperature of the water, so either they put a thermostat or something down there that would give them a reading on the surface, or somehow they capture the water down that deep, like send a tube down that they can remotely open, and then, or maybe they're scuba diving, I don't know, but something like that. But these are the temperatures in degrees Fahrenheit. It must be Celsius, right? Right. So the 20 is a fairly, 20 to 25 is a fairly comfortable temperature, but you get down a certain point. Has anybody ever done scuba diving? So if you do scuba diving, you go down after a while, and there's something called a thermocline. There's a layer at which the upper water that's warmed by the sun mixes, and then the lower water down below does not. So you come down, and suddenly you hit this wall of cold water, and it's like, oh, here's the thermocline, right? And then below that, it's quite a bit chillier. So maybe we're looking for a nonlinear effect. So I've loaded that data in there, and I'll hatch it so the commands run. And we want to try to predict temperature based on which day it is, perhaps. These days are not very far spread apart, so there's not going to be much of a seasonal effect there. But in meters, and figure out how can we use meters to do that. So here's the box plot. Does there appear to be much of a day effect? Not much of a day effect, right? But a lot of variability within days, from 5 up to almost 25 Celsius. Right? In terms of meters, here it is. And so, in trying to do this, I realized something. So the box plot puts equal spacing at all the numbers you give it, all the categories, right? So 0, 1, 2, 3, 4, 5, 6, and then 9 is immediately after that, and then 12 and 15. Right? So that between here, there's some big drop off. Right? And this does show the obvious big effect by day, but it's not exactly, the scale. So if we do analysis of variance to look at days and factors, you could, just a histogram also of temperature, it's not going to be particularly normal, but we don't really need temperature by itself, Y variable to be itself to be normal, right? It's the residuals have to be normal, right? So this one's not going to be normal because it's spread over such a range of depths that make a big difference, right? The previous plot, right, is there's this changing mean, and really, is it normally distributed within these categories after we adjust for the, however we're going to model the mean change in there. Right? So we're not really concerned that this is not normal, but after we fit models, we still want to look at residuals and see if they're normal. Days doesn't seem to have much of an effect, as predicted. Meters, though, as a factor, does. If you reverse the order, meters, you get a significant effect. Again, this version of the default does not make any difference in those. This thing it doesn't make any difference because this is balanced. There's one measurement at each depth on each day. You could possibly have done 2 measurements on each day, right, and get some replication in there. But, it might not have made much difference, right? Think about what the sources vary. Would the temperature measurement be substantially different at 2 different time periods kind of close together? probably within an hour of each other. Probably not that much of a difference. A little bit of variability, but not so much. If we wanted to test, so in the summary, the linear model summary of days, none of the days really seem to have much of an impact. It's only varying things by as much a quarter of a degree, whereas all the different meter effects are much bigger. Right? And there might be some here that maybe you don't need all of those down there. There might be some group of, after you hit that thermocline, there's not much mixing in the lake, and it's essentially dead down there. So there's not much change. So maybe that would be something to think about later. So if you did the ANOVA to compare these two things, you will get a p-value for testing whether there's a significant day effect, right? That was the same as the line on the ANOVA table for just that model. The days are not significant, right? So if you wanted to do some of these things by hand, right? So one aspect of the older textbooks from in the past, before computing, they really showed people how to do computing on graph paper, right? Or on accounting paper, right? What do you write in each column, and what do you calculate by hand, and write here, and then what do you take the differences? And so it's a very different style of textbook where you'll have pages that are just, here's how you do calculate things. So to do it by hand, we could calculate the average. And so what that will do, here's the data, right? Oops, it has the whole thing here, where I've added other columns. But this first one is just adding in y bar all there. 15.9 is the average temperature of all these measurements. There's a difference by day, a little bit of difference by day. And as you notice in R, it just keeps it has the labels on there, right? And so if we repeat that, days. So 15.13 is in August. So I just kind of realized something. So how is this data set organized? It's the July days are first. So one thing we actually want to do, right? This repeated thing, we're putting what this thing going to do? This little repeat here will repeat one temperature 10 times and another temperature 10 times. So I put there. However, the days are taken as alphabetical. So August becomes before July, which is a problem. Right? So we want to actually change this. Sorry, levels of days are this. So we really want to reassign this to make it work out. I don't know why I didn't notice this before. 25 July, 30 July, 31 July, and then 01 August, like that. So now I think when we do the split, oh, it didn't change it. So days is a factor of days. And we'll put the levels to be this thing, right? Let's see. So now if I take the numerical values of those, no, it didn't switch it. I'm going to get rid of this, the old thing, and now if I reattach, so let's see, rot.days is going to be, what is days? How is days work? What are the levels of days? Is that, that worked, okay. So I'm going to change rot.days to be that little thing days, right? So now what are the levels of my data frame? Right, so that matches now. So now if I do the numeric thing, right? Okay, so I would attach rot. Right? Okay, that's fine. And now, okay, let's remove this so it doesn't give me any problem. Right? So have to use that one. I don't know why. Anyway, I need to figure that out, but there would be this issue of getting it to work out. Anyway, so that would put the days on there. Let me just run that anyway and see what, did it change anything? It still has the 15.3 first, which wouldn't be right. So you maybe have to go manually, kind of do a little more programming to make it work out. But you could calculate the total sum of squares. You could calculate the residual sum of squares. And this number is actually a little bit wrong, right? It must be wrong because the order isn't right. If I do the subtraction, yeah, I do get this other value, 2.243. That matches what we had back over here in the, ANOVA table, if you take the difference of these things and the sum of squares. So anyway, you can do things by hand. I guess the message is you have to be careful with that. But let's continue with the analysis anyway, because that's more interesting. Here's the plot. Right? What's the difference between this plot and the box plot? In the scatter plot, it has the actual values of temperature rather than temperature as category, right? So it has spread these three out, right? So once you hit that kind of thermocline, it stays pretty constant down there, right? If you fit a linear model, right, that's the linear fit to these data, right? Obviously, there'd be some problems with that, right? If you put meters squared in there, right, you can put the points in blue on there where the 1, 2, and this is where the prediction would be for the quadratic, right? So it certainly looks better, right? Well, mostly, right? It hits this one, it's closer to these two, kind of further away from some. One thing about the quadratic is it's determined by the entire curve. There must be a point outside of that because we don't see it there. So we can change these things. We can do a y limit. Say, let's do 0 to 30. All right, and run that. Right, so that's what our data. We'll see the entire line now. All right, so there's the prediction line. And these points, right, to the, right. One thing about fitting quadratics and curves is the entire, all the data points determine where the curve goes. And tail effects, it has to follow that quadratic in here. And it has implications, what happens down here to fit the quadratic influences what it looks like way up there, right? So the extremes on either end can cause funny things. But this doesn't seem to quite fit either, right? We'd have these chunks of residuals that would be bigger and smaller. Right? So what about a cubic? Right? The purple ones are the cubic ones. Right? And they are kind of well, that's fine. That's pretty close. This one's kind of similar. It's kind of moving up. So it's still kind of not fitting it exactly. You can really kind of go overboard and fit, four-way things, and the little gray ones here are those, or even to the 5th power, and then those, go there. So you can see where these different. It's kind of making small adjustments as you add these higher order terms to try to fit this curve. Well, do we get a significant better fit as we add these models? You could look at, the first one going from linear to quadratic. That certainly seems not surprised there. Going from quadratic to cubic, it also has a significant fit. Going from cubic up to the 4th, okay, that one, the one with the 4th, which was the gray ones, had a significantly better fit than just the cube. So a 4th degree polynomial, really, for this data set? It seemed a little bit, it's adding a lot of higher order terms, kind of a fancy curve to fit this model. And, but then the question becomes, does it actually fit so well? If we do a residual plot, right, we can plot the fitted values under the 5th model, fourth model, and the fitted residual values under the mod 4, and see what those look like. Maybe line, horizontal line at 0, and a little dotted type here. We still see that, you know, some of the kind of a pattern to the residuals, and it just doesn't fit some things. There's something more going on there, and so that it's not completely satisfying because the pattern that's still there. There's only one x variable with the cubes and everything. So we might compare it to just a linear fit with temperature versus a different mean at each of the meters. Right? So that would be this meters just as a factor, as represented basically by the box plots rather than the scatter plot. And so if you compare any of those models to the one where meters are different, the one with a different mean for every meter is better. So even though the quadratic, cubic, quartic fit better than the preceding polynomial model, none of them do as well as a separate mean for each group. And there's certain key variability it just doesn't get. So you can build up models and get kind of complex, but still there can be something fundamentally off there. One way to compare all these things, you can compute AIC or BIC for a whole bunch of models all at once, right? If you save them there. So AIC of all those. The best model ends up by far being this one with different meters, right? AIC of 29 with a separate mean for every group. But among the quadratic, you know, the polynomial ones, getting down here to the fifth one is preferred there. BIC has a bigger penalty for adding parameters. And BIC would stop kind of at the fourth polynomial, right? There. But still, it would say, you know, there's a different mean for everyone. It doesn't really fit these patterns. So you might have some try some interactions. The question then is, can you fit an interaction? And if you do the linear model with the interaction between a mean for every meter and days, you get this funny stuff, right? What's happening when we try to do this interaction? Remember our table of, there's only one measurement at each depth. So if you have an effect for days and meters and an interaction between all these, essentially you have a parameter for every single measurement. Right? And you know, it's just reproducing the data. It's not summarizing, it's not reducing to any useful way. And as a consequence of that, it has no way to calculate standard errors, standard deviations. There's zero residuals because it fits everything perfectly. Right? If you did a plot of meters versus the fitted values of this, where was that one? This thing, this linear model here, this one. Right? If I put that in there, it, not meters, you do temperature, right? Right? It's reducing the data. That is a straight line. It should be beyond there, you know, exactly. And so you can't get estimates there. If you do run the analysis of variance with a model that big or that, what does it look like? It gives you a warning, perfect fit. It gives you meters, days, and then the interaction, and nothing for the residuals because you have a parameter for essentially a parameter for every observation. If you compare that to just the additive model, I don't think it's big, you see that you get the same sum of squares in both places. And what was before called the sum of squares interaction is in the additive model what gets called the sum of squares residual. Right? So this one, where you don't try to estimate that other factor, just have main effects, the additive one, you can test these different factors versus that, and that's essentially what's done. But you don't get any significance testing if you're fitting a fully saturated model, and there's only one replication per time. So what else could we do with this, right? Well, in our little discussion, I didn't really think about this before so much, but there is that biological thing of the thermocline. So at some point in that lake, the temperature is always cold below a certain point. Instead of taking the depths at 9, 12 and a half, and 15, if we said, okay, essentially it doesn't matter how deep these are, either we cut it off here and say we're only going to use the ones before that point and not keep going where it's constant. Essentially that'd be kind of claiming it's piecewise, that there's kind of a flat part here and then a curve. We probably could fit this curve better, and some of the problem could be these two out here. In fitting our quadratics, the fact that these are out here means we have to flatten out at this point. That's going to have implications for all the coefficients in the model that determine how this curve goes. So these cause problems fitting in the middle and back up here as well. So maybe cutting it off at the thermocline for the lake would give us a data set where we can fit a curve that'd be a little bit more meaningful back there. The other place I've seen this type of thing happen is at George Washington University. There's a Center for Paleohominid Studies. And so it's looking at comparing they study orangutans and mountain gorillas and prehistoric skeletons. And so, and chimpanzees and other primates. And so they were looking at the growth of individuals, right? And they would get some individuals who would be very old, right? And then some that were very young, and measure their while they're alive, measure their skull and weight and other things, and height, right? And it wouldn't be, there'd be a curve. It would go up and then down. But trying to fit that with one model was really hard, because there'd be a growth phase, right? There'd be kind of a fast growth phase, and then it would come down, and then it would trail off. As people and animals age, they kind of shrink a little bit. Right? Gravity eventually wears down on everybody, so and muscle tone after a while gives way. Right, and so it went up, and then it would go down, and the trying to fit one curve over all that, in that application, you kind of run into the same thing. It's like, well, if you're actually going to try and fit that curve, it needs to be a high degree polynomial, but trying to fit this tail out here has implications for everything through the line, and so it created funny effects where there'd be kind of an upswing or something like that wasn't biologically very satisfying. So some of these things being kind of hard to do. There's an area called semi-parametric models or generalized additive models. There's other ways that curves are fit to patterns like this, to get fits that are not so, they are statistical, but they're also more machine learning type of fits, more adaptive. Sometimes they put a little spline or a little knot in here and say, okay, well, we're going to do a little piecewise linear part here, or piecewise quadratic in this, and we're going to put another one here and do a little piecewise thing here, and another one here, and a piecewise quadratic. And then we're going to do something to control it so that the predictions become smooth. There's other ways of fitting, and so something like this could be done. So we've done a lot. We can fit things pretty flexibly, but there's another world in more advanced methods that would do some things, and maybe we'll look at some of those as we go on. But anyway, that's this example. Right? A second example we can look at is one from our book. There's an exercise 1420 in here in the book that concerns weight loss. So what are the variables that are in that? Exercise 1420 has different diets. Right? Subjects, they put on randomized to certain diets. Male, females reported. The age, the BMI, where they started, and then weight loss after 24 weeks, I guess. And the question then is, which diet impacts weight loss? Okay. And is there a difference between men and women in terms of the effectiveness of any of these diets? And so this one, and there's also this quantitative factor of age and BMI. So we can start with analysis of variance, two-way analysis of variance, with sex and diet as factors, but then these quantitative things might come in. And again, we're going to try and look for a model that tries to fit well and gives us an answer to those. Right? And so here's the diets and the sex. And I don't know, there's some obvious imbalance by looking at this that you wouldn't know until you looked at the cross tabulation. For some reason, this study only had a small group of females and a large group of males. I didn't see a clue in the description of why exactly it was like this, but that's kind of a funny thing, I think, to not comment on. Analysis of variance, diet and sex, and a possible interaction. Right. Diet is statistically significant, but there does not appear to be an interaction with sex here, female, male, right? And the main effect here, right? So we could test, is there a difference with sex? So in testing some of these things, right, if there had been an interaction, right, how do you actually test? Is there an effect of sex? Is there an effect of diet? If there's an interaction, we really want to do a nested ANOVA. Right? So we would want to copy this over. And we would want to do a model that just has a diet in it. And that would fully test, is there any effect of sex at all, either through the main effect or the interaction. And if we run that, the answer is no. There does not appear to be a difference in weight loss between men and women in this study. Right? Is there an effect of diet? Well, if you only have sex in there and then diet enters as a main effect or an interaction, this one would test comparison to that other model. Is there, oh, it says that there is no effect of diet, which is kind of funny.
Well, look, the ANOVA for just the the p-value for just the diet was like, it was we rejected it, but it was like
it wasn't too
4.
big, yeah.
It was
0.04. Right. So if you did the analysis, ANOVA, just out of curiosity, only with diet, right? One more there. Maybe just one? You know, you go, right? Diet by itself is just barely significant, but adding in that interaction seems to kind of mess things up because there's not much so. It surprises me a little bit, but you're adding extra coefficients, so you have to get a bigger, you can get a bigger standard of error. Yeah.
But a situation like this suggests that maybe an alpha level of 0.05 isn't the best. Maybe, I don't know, because it seems like when you take into account sex, it's not significant. So maybe that's saying that like 0.04 isn't significant enough to reject a null in this case. I don't know.
So, right, there's something funny about there's only certain women in there, the men. So, you know, you kind of worry about generalizing to the population when there's something funny in the design. You know, 0.05 is fine, but there's very little difference between something that would be significant at like 0.045 versus 0.055. Right? They're both pretty rare if the null hypothesis is true, right? But so reporting the actual p-value and then having a discussion about it would make more sense. But it's so as you add sex with an interaction, right? There's 3 diets, so you have to add 2 coefficients for the interaction and 1 for the main effect. So adding sex in this way adds 3 parameters, right? So degrees of freedom go down, right? We don't have a really large study anyway, so that's hurting degrees of freedom in testing, right? So you're adding parameters that don't help. It could hurt the other evaluations as well. So So let's kind of look at plots. Does this confirm what we want? A box plot with the different levels. Right, so here's female and male, and then the 3 diets: carbohydrate, low carbs, low fat, Mediterranean. Apparently there's a diet effect, right? There's kind of differences within males and females and so on. But the male to female, I guess, doesn't look particularly different. There's a command called interaction plot. There's also a command that I don't necessarily remember all the time, but my notes had this one in it. And so this plots means, right? And so it's means of the 3 diets. So there's low carb, low fat, I think, and Mediterranean. Let me see. Let's see. Does that help us at all? I plot that one. Yeah. So low carb, low fat, and Mediterranean in there. And here's the male weight loss and the female weight loss. And the female weight loss does look less at each of the points, but there's only 15 females in each category. That sample size could mean that this difference is not significant. But kind of the average, kind of the midpoint of those, there seemed to be a big change. The low-fat diet certainly seems to be have less weight loss. The low carb, the Mediterranean seem to have more weight loss. You can do it the other way and get a different picture. So female versus male. It's kind of flat, the Mediterranean, bigger for low carb, bigger for low fat. But that could be not significant due to just only 15 in that smallest group in each of those categories. So if there's not, you could fit a main effects interaction, sex is still not there, so you might want to take that out. Residuals, you could look at residuals, right, of a particular model. And the residuals there's only categories in there, so there's only these things. But each group seems to be kind of centered pretty well, kind of around there, plus or minus. So it's not like the other case where some groups were completely missed by the things. Yeah.
So in general, when we're plotting these interactions, we're trying, if our lines aren't parallel in general, that should suggest an interaction. But in this case, where we have so few samples, that it's tough to reject. It's tough to claim that there's an interaction because of a few female samples.
Well, there's that, but there's so looking at this distance, is this distance about the same as this distance, about the same as this one? And there's a little bit of difference, right? That would be an interaction. And so there is a small difference between these contrasts here, but the small sample size makes it hard to be significant, right? So if this one went kind of flat down here, so you'd have a big and then medium and small comparison, maybe that would be significant. Or looking at it, the other plot, right? Female to male is going up, right, in here. And right, so this difference is kind of big. These two differences are not too different from each other. So female versus male, how much does it climb? It's kind of moderate here, and it looks bigger here, right? And if we had 150 females instead of 15, maybe that would be significant. Well, so we could look at, so another thing that could be obscuring the effect of either sex or diet would be differences in BMI and age, right? So if the males and females have different ages, if they had different BMIs, and those two things are affected to the weight loss, then it could be obscuring things to some degree. So we could look at correlations in plots, but I'm just going to jump to the plot of weight loss versus these factors. And what do we get? We do get a significant impact of one of the diets, at least. The low-fat diet was less. But BMI and age and sex just do not seem to adjust things. They're not significant, right? Which would suggest that they don't play as much of a role. And many of these things you think that they might. In order to compare the diet effect, the diet had 2 levels. So is there any diet effect at all? We could fit a model without diet and one with diet, and then use ANOVA. And yes, there seems to be a significant diet effect. And we know that it's the low-fat diet that is less weight loss than the other 2. Is age related to weight loss? We could plot it, right? But we could also add some characters in there to look at the male, female, or diet. Right? And so this sets up the plot, and then this is going to put points in there. It's going to put in red and blue dots by sex, and the character is going to be male and female. So these are the data. Right? Not much trend versus weight loss. Males and females seem to be kind of equally scattered in there. There's not kind of a separation. And so that's why we're getting no apparent effect in this particular study. And so any of these medical studies, if you were in the field of trying to judge whether there is an effect of something, you have to look at which subsets of the population are used in there, right? So maybe one of these diets would be really effective on people that are grossly obese, right? In a certain age range. Or maybe this study is taking a small subset where there's not as much of a female-female difference. But that doesn't mean there's not a difference overall or in other groups. So if you had to synthesize ideas from 10 or 20 or 100 studies of similar topics and come up with some conclusion or recommendation, there'd be a lot to consider. And the funny thing that this had only 15 females in some of those groups and many more males is something. We can also compare BMI, right? BMI in the 20s and lower generally are better, right? Down lower 20s, so these are overweight or obese. And again, not much pattern here going one way or another. Maybe there's a slight trend, but nothing very big. Males and females, are they really separated? No, I mean we're not getting significant effects here. So this is, one of these other the other one was a little frustrating because of the polynomial curve being quite a bit. This one's a little frustrating because we have these variables that don't seem significant. Right? So what could you do, right? And so I don't have a great answer how you could do better prediction in this. One conclusion is just keep it simple and say the low-fat diet doesn't reduce weight as much as the other 2, and that's the estimate of the weight loss. There's no real control group, right? One of our problems from the homework. Well, no, that's my other class. So there's an example with no control group, so can you judge how effective these things are? Well, without an actual control group where you just measure people and then measure them 24 weeks later, it's hard to say if these diets are really better than just telling somebody, you need to lose weight, right? Or here's your weight, that's a high BMI, you're overweight. If you just tell somebody that, would they behave differently for 24 weeks or 24 days if that's what it is? And you can see what impact that has on them. So I thought, maybe you could convert age to categories. Sometimes you get a difference by category. Maybe you can see, I don't know, even that doesn't look too promising there. Or BMI to category, it doesn't seem to be any pattern at all. Another thing would be to change the variables. Right? Weight loss is in pounds or kilograms, and BMI is transformed. Right? It's weight divided by like height squared, essentially, right? So it has different units. So trying to predict weight loss in kilograms versus age or BMI is just mixing things with different units. So maybe changing everything to pounds or changing everything to, changing the weight loss in terms of change in BMI categories. Right? If you go down to one category in BMI, maybe that's more related to the BMI you started at or age. So maybe there's another form of the variable that would work and give you something more significant. And so again, this age, this one, weight loss versus BMI, kind of as a fraction, right? Thinking that individuals with larger BMIs are more overweight, so maybe it's they lose weight faster, or if they change their diet, it's going to have more of an impact. But still, age and sex and are not significant. One of the diets, again, is significant. So it doesn't solve the problem in any way, but you might support transformation. So every once in a while in regression, you try your different things and it doesn't really work out so well. At least in this one, we could come up with a positive conclusion that there is a difference between one and the others. And we tried the other things and investigated, residual plots, other different scatter plots, possibly thinking about transformations. But that seems like the best that could be done at this point. There wasn't a significant interaction, but I might be tempted to look at just the males because they were the larger group and see what replicates in there. Maybe among the males, age or BMI makes more of a difference. From the pictures, I'm not too hopeful, right? But it could be possible that including the two groups together, even with some bit of modeling of the difference, would kind of confuse things a little bit if they have very different effects, right? Things can kind of average out. So if the females had a relationship that went up and down, and the males had a relationship that went the other way, and you put them together, they could balance out to nothing. But there could be kind of a funny interaction that you wouldn't see. So you could report we have one test, there is a significant difference between these, and then some other explorations. But that's essentially what I have for today. A couple examples to look at where things didn't work out exactly wonderfully well, but it's the tools that you would use to investigate it, I think. Yeah.
I just have a quick question about when we use the box plots. Essentially, if we're using box plots of an interaction, if we're seeing box plots that are very similar in terms of they don't vary much from one another, is that signifying that there isn't much of an interaction, essentially?
Yeah.
Because I noticed that in this case.
This case, there's not much difference.
Yeah.
So the females on the left, so the medians, these are the medians and the means. There's also a possibility that there's one or two outliers that would be causing things, affecting results. So, further investigation could kind of look at some of those.
But in general,
these look kind of the same. These look not too much different. These are a little difference there. But if there were an interaction, you would kind of see.
Mostly we'd see a bigger difference.
Yeah, you could pick out one of the diets and compare the males and females, and you expect to see a difference.
Yeah.
Somewhere.
Yeah.
Okay, so on Friday we'll look at a little bit of enhancement to things in chapter 14, a little extension before going on into serial data.